Ladies and gentlemen, welcome to Physics Rocks. It's true, it is the big one. It is A2 Physics, and it is the very, very last topic of the course. We are into fundamental forces, fundamental particles, and how it all works. Be prepared for words like quarks, like bosons, fermions, and interchange particles as we get into the absolute weeds of what makes up stuff. So to get started though, we need to understand that there are essentially some fundamental forces. And this word fundamental is going to appear quite a bit this evening. That by fundamental we mean that there's no underlying structure to it, that there's nothing simpler. Now, scientists, generally speaking, are a little bit tentative about the word fundamental, okay, because we've had our hands burnt before on this, that you had the idea that the atom was fundamental and it was broken and shown to contain protons and neutrons, and then they were thought to be fundamental until they were broken to give up their quark structure. So when we say fundamental, we mean there appears to be no underlying kind of causation or no underlying particle or no underlying system beneath that which we can observe. Okay, now in terms of forces, what you're looking at is you're looking at the four fundamental forces of nature. 1, 2, 3, and there are 4 of them. Now you might be familiar with the concept of, say I have an object here and it strikes another object later on. Okay, goes pump, hits off there. Then that could be considered to be an impact force of some description. But if we look down to the absolute tiny level, what's actually occurring here is that the charges, the positive charges here and the positive charges here, as they interact with each other, cause an electrostatic repulsion. And that repulsion is what sends this one off this way, conserving momentum, conserving energy, and doing all those necessary things. Okay, so once you break down all the forces that there are and all the interactions that there are going on, you end up with 4. Okay, the first one is the electromagnetic force. And as the name suggests, that is a theory that combines magnetism and electricity, electrostatics and magnetics together. Okay, and the equations for these are absolutely brilliant. The Maxwell equations bring these all together. That's next year when you go to when you head out to university and do amazing physics there. Okay, so let's get ourselves on. Electromagnetic force, that's number 1. Number 2 is also a force that you'll have heard of, and that is the force of gravity. A gravitational attraction, or gravitation, whichever way you want to put it. Okay, the force of gravity interacts with us in our daily lives all the time. We're aware of it to the point that you're probably sitting down right now, and if you're not, you're standing up, and you have to put some effort into that because otherwise you'd fall to the ground. Okay, so gravity is pulling on you. Gravity is by far and away the least powerful of these forces, but its infinite range is what gives us that kind of sense that it's everywhere and it controls huge objects, and large objects can exert very large forces. And because we happen to be very small objects stuck to a very large object in the form of the Earth, gravity seems to play a very large part in our life. But it doesn't take us too far, or it doesn't take us much distance to get away from the Earth before the gravity of the very large Earth stops being a particularly interesting concept. Okay, now then we're into 3 and 4, and these are ones that you're less likely to have come across. Now, if you find yourself inside a nucleus of an atom, which is, let's be honest, reasonably unlikely, but let's imagine that you can shrink yourself down with your physics knowledge, and you find yourself in this dead simple nucleus, plus plus. 2 pluses, so 2 protons and 2 neutrons in here. The question that should enter your mind from the moment that you start studying the nuclei is, why is it that 2 positive charges can coexist at a distance of a femtometer apart? 1 by 10 to the minus 15 meters. These things should be flying off each other, especially given that the person giving me the tutorial here literally just said that the reason things bounce off each other is because pluses come in contact with pluses. Well, this is about as in contact as you can get. And the reason is, at very, very, very short ranges, okay, around about the range required inside a nucleus, there is another force. Okay, and that force is extremely powerful and binds these 2 together, okay, once they get close enough. And it's called, wait for it, the strong nuclear force, in a moment of exceptional foresight to understand this. Now, if we were to draw a graph of what would happen to a proton being brought towards another proton, and if we were to have, I don't know, like repulsion in some form of measurement, repulsion force in some appropriate unit like newtons on the y-axis here, and then distance on the x-axis, what you'd find is that at reasonably large distances, the repulsion force is negligible because it's a it's a 1/r squared thing. But as you get further and further away, the repulsion gets lower and lower and lower. We've done this, the Q1 Q2/r squared concept. Right, but as we get closer and closer and closer and closer and closer, this becomes progressively larger, okay, because it's a 1/r squared relationship. So up it goes here. But there comes a breaking point. There comes a point when we get down to the width of a nucleus. We get to that 10 to the minus 15 number, that we've provided enough force to crush these things together. This graph just suddenly nosedives, okay, and becomes attractive. It heads into the negative, so there's negative repulsion. This is attractive then, and this holds the whole thing together. And this little section of the graph, this is the domain of the strong force. Okay, and it's the reason that atoms stay together. Okay, and then finally on number 4, we have, if we have the strong force, then we have also got something called the weak force. It's actually called the weak interaction. Okay, the weak nuclear interaction. And the weak nuclear interaction is a requirement for, do you remember in an unstable atom that you can have neutrons that just randomly become protons and fire out an electron, and that electron was called a beta particle, okay, in beta decay, little beta. Yep, and that came out screaming. Now, how did that happen? Well, the reason that happened is because there's a fourth force that also operates inside the nucleus, and it's called the weak nuclear interaction. Okay, these are our 4 fundamental forces, and the standard model, or at least the particle physics model that we're going to use this evening, says that each of these forces has a force carrier. Okay, that there's a particle that carries that force. Okay, so we have some form of force carrying particle. Now, rather than say force carrying particle, because that's a mouthful and also is understandable by the general public, we're not going to call these force carrying particles at all. We're going to call them gauge bosons, because that makes sense, doesn't it? Okay, and a gauge boson is some form of particle that carries these forces. Gauge bosons by themselves are fundamental, because if they weren't, then the force that they were carrying wouldn't be fundamental, because there would have to be some form of force putting them together. Okay, so let's get stuck into it. The electromagnetic force, the particle that carries the electromagnetic force, we're already familiar with, and that is the photon. Hence, it's called the electromagnetic spectrum. You've seen that before. Okay, so the photon carries the electromagnetic force. Everything else here is probably a little bit new to you. The strong nuclear force is beautifully named that its exchange particle, or its force carrying particle, is called the gluon, because it helps glue the nucleus together. Okay, Lucifer, does today's stream cover positrons? We will talk about positrons at some point during the course of this stream. It will probably be in passing more than the actual discussion of what a positron is, but we will definitely mention it. The weak nuclear interaction has 2 different bosons. They're called the W boson and the Z boson. Those are named after different models in which they kind of work. Okay. I'm not going to touch too much on the weak nuclear interaction tonight, but we may come back to it at a later date when we start looking at beta decay. We're in the last topic, but this is certainly not our last video. And then finally, gravity. Gravity is an issue. Gravity currently sits outside this fundamental forces model that has exchange particles. Okay, The discovery of the Higgs boson, I'm sure somebody's thinking about that, was the reason that give a particle that explained why things have mass. Okay, but that's slightly different to a particle that would actually transfer gravity between two objects. And what I mean by that is, imagine I have an object in space over here, and I have an object over here. Now, we know that those two objects will gravitationally attract each other in such a way that they come this way. But how do they know they're there? And this model suggests that there's a little particle that travels from object A to object B, and then back and forward and back and forward. And they're exchanging these particles all the time and absorbing them. And the absorption of these particles is what's drawing them together. But like if I had a large positive charge that was throwing an electron over here and this one was throwing it back, that they kind of tug each other together because of the negative charge in here. That's sort of the idea going on here. Okay, so the particle for this is theorized but has not been discovered. So Nobel Prize is up for grabs if you can discover the graviton, and it is, at the time of recording, theoretical at the moment. Okay, and this breaks us into our gauge bosons. We have photons, we have gluons, we have a W boson and a Z boson. And if you're asked to name gauge bosons, there are only 4 for you to name: photon, gluon, W boson, Z boson. Graviton has not been confirmed yet, and therefore shouldn't be quoted. All right, so we've got our 4 fundamental forces in nature, and we've got our 4 exchange, or our 5 exchange particles if we want to talk about these. Okay, so we've got forces, and that's part of the universe. That's kind of the makeup of how everything interacts. But what do we mean by interacts, and what are we actually putting our forces on? Well, we're putting our forces onto stuff, aren't we? Yeah. So the universe is made up of stuff. Yeah, we can't say stuff, but we're going to say stuff anyway. Stuff, or matter, if we want to be nice about things. Now, I don't want to say matter too much because there are places that we have antimatter. Now, antimatter sounds like some exceptionally exotic, wonderful, amazing thing. And well, it is, because it's really uncommon to find, but at the same time, it's not particularly amazing. Okay, one of the kind of key thing about antimatter is that if I have a particle, let's call this particle X, okay, and I could somehow make its antiparticle, which would be X minus. Now, I'm going to put a little bar above that, okay, like this, because it's not to be confused with its charge, okay, because some antiparticles have the same charge as their regular particle. We'll talk about that later. So if I have particle X and particle X minus, okay, or anti-X, so this would be, we could probably name this as X and this as anti-X. Well, if X ever meets anti-X, they will destroy each other. They will annihilate each other. Okay, and the result of that annihilation is that they will both be destroyed, but because of conservation of energy, maybe a photon is created, or some object that actually has the energy that was contained within these two things. Importantly, that if X has a mass equal to m, then anti-X will also have a mass equal to m. It does not have negative mass. Mass is a scalar quantity in our universe. Okay, so yes, thanks, Michael. Why is there a bar above the bottom X? It signifies that it's an antiparticle. Yes, it's the antimatter equivalent of X. Okay, if X has a charge of, say, +1, then anti-X will have a charge of -1. If X has maybe a baryon number of 1, which we'll talk about later, then anti-X will have a baryon number of -1. Okay, depending on what X actually turns out to be. All right, but it is important to understand that they are still particles with mass, that they are still traveling through the universe, that they can still interact with each other, or they can interact with other matter. They just can't interact with each other in any way other than to annihilate. Okay, do I accept donations, Mike? No, just your appreciation, and likes and subscriptions are my fuel that I need. I'm a massively well-paid teacher. All right. Now, the great thing about physics is that lots of things run in reverse. Okay, that we can do something called pair production, which is if I take a photon with sufficient energy, and the sufficient energy would be, E equals 2mc², because I need enough to make two masses. I need to make an X and an anti-X for what I'm about to do. And I subject that photon to some situations, like I pass it near a nucleus or I do something along those lines. What can happen in certain situations is that the photon can undergo what's called pair production, which is that it can create a particle-antiparticle pair, where X is created and anti-X is also created. Okay, and this is not particularly uncommon. Like we see electrons in their antiparticle, the positron, being created above thunderclouds. We see that happening on Earth. It's not something that needs to happen at the Big Bang. It's not something that needs to do that. We see radioactive particles do this all the time. We see beta positive decays as opposed to beta negative decays happening, where positrons are emitted from nuclei as opposed to electrons. Okay, so we get a quark, antiquark, or we get a particle and then its antiparticle pair here. And they'll head off. Now, if X minus runs into something that looks like X again, it will annihilate, and that's the end of that matter. Whereas X here is now perfectly content matter and will travel off into the universe. Okay? Is that all right, everybody? I hope that's okay. I hope that sort of made sense. All right, so that's a brief overview of antimatter. And the reason that we're going to need to talk about that is when we're talking about all of our next bits of stuff, we're going to have to keep in mind that every bit of matter that we're about to discuss has an antimatter equivalent. Now, be prepared because jargon is on its way. Right, so if I take, say, something like a proton, which was previously thought to be a singular particle, and I smash it open, what I discover is that my proton has in fact got three little particles living inside it. Okay, three little hitchhikers that live inside it. Okay, let me get this scaled right. I'm just copying these from elsewhere, so it makes it a little bit more difficult. Okay, and these little triplet of particles are called quarks. And they come in different types. There are a variety of them. There's the up quark and the down quark. There is the strange quark and the charm quark. Strange has an R. There is the top quark and the bottom quark. Now, for the purposes of what we're doing, we're not going to look too much at these quarks because they're what are known as the next generations of the up and down. They differ from the up and down quark in that they are a little bit heavier and they can decay into different things as a result of that because they've got different energies, by E equals mc². But they fundamentally do the same thing. The up quark has a charge, and let's call that Q. And its charge is plus 2/3. The down quark also has a charge, and its charge is negative 1/3. Okay, so if I want to make a proton out of three quarks, I will need an up quark, which will give me 2/3 charge, another up quark, which will give me 4/3 charge, and a down quark that will give me negative 1/3 charge to make myself a total of plus 1. Okay, does the strange quark explain strange stars? That is something that I'm not 100% on, but I'm going to assume that the naming convention is more than just a coincidence there, Lucifer. So I'm going to say yes, but with a tentative. I'd like to check that one out first. Okay, so to make a proton, we would need an up, up, down. Now, those of you who are paying attention in the chat, let's imagine we wanted to make a neutron. Again, we would need three quarks. Which quarks are we going to need to make a neutron? Remembering that a neutron will be made of three quarks and will have an overall charge of 0. Okay, so we will have an overall charge of 0, and we'll have 3 quarks in here. So to make that, I'm going to use an up quark, and then I'm going to use 2 down quarks. Okay, which will give me up, down, and down. Well done. For a couple of people in the chat that got that. Nice one. Nice one indeed. Okay, so up, down, down for that will make us our neutron. Okay, so what we've done is we've used 3 quarks to build basically the overall picture of the universe, because we can make protons and neutrons. We've got the nuclei of essentially everything. We'll need to deal with electrons soon, but not quite yet. So if you're using 3 quarks to build a particular material, then what you have done is you have built a baryon. Okay, you become a baryon. So anything with a 3 quark structure is a baryon. So 3 quarks gives you a baryon. Okay, so I've left a bit of space over here because we're going to introduce a new number here. We had Q, which was the charge, 2/3 and -1/3. Of course, that's relative charge compared to a proton. Just want to make that clear. So B here is called the baryon number, and the baryon number of an up quark is 1/3, and the baryon number of a down quark is 1/3. And the reason for that is that once you put 3 baryons or 3 quarks together into one of these situations, you will get a baryon number B equal to 1. And it's a bit like binary. If you have B equals 1, you are a baryon. It's a confirmation system. So B equals 1, you are a baryon. All right. So let's talk about, hey Matthew, no bother at all. Good to see you. Now let's imagine that we have a situation where we have the antiparticle of this, okay, because quarks make up matter and they have their own little antiparticles. Then we would have to have an anti-up, an anti-up, and an anti-down. So let's make all these into antiparticles, and let's make some antimatter. Let's get an anti-up here, an anti-down here, and an anti-down here. Okay. So let's see what we've got in this case. Now the thing about antiparticles is that they have the same mass, but they're going to have opposite charges. Okay, so let's get rid of these bottom ones here, because we're not going to play with those just yet. And let's replace them with anti-up and anti-down. Okay, so the charge on an anti-up is going to be negative 2/3. The charge in anti-down is going to be plus 1/3, the exact opposite of their matter equivalent. Their baryon numbers are also inverted to a -1/3 and -1/3. Okay? Are we happy enough with that situation so far? I hope so anyway. So when we look at our proton here, we now have it made of antiparticles, which will make it an antiproton. But putting together our stuff, our antiproton now has a charge, Q, equal to -1. It's got the opposite charge of the original proton. Do we see that? So that's 2 -2/3, which gives me -4/3, and then we add 1/3 to it to give us -1. The neutron, well wait, it's still got no overall charge, doesn't it? Because 2 anti-downs is plus 2/3 and an anti-up is -2/3. So the neutron doesn't really look that different. However, if this anti-neutron were to meet a real neutron, they would annihilate, releasing E equals 2mc² of the energy that they had. Okay? So does that mean when you add them, they aren't a baryon? That a boy, Lucifer, now you're looking at it. Okay, so once we get these 3 in here, we get -1/3, -1/3, and -1/3, and we get B equals -1. Okay, now this is important. There's still a 1 there. So you're still not a baryon. But you have to temper that with you are now an antibaryon. You are the antiparticle of a baryon. Okay, so 3's a bit random. What if I were to just do, like an up-down quark? Right? That wouldn't be an antiproton anymore. Let's not mislead people. If I was to do an anti-up and an anti-down, what would I get? Well, an anti-up quark has -2/3 and an anti-down quark has +1/3. So that would give me a charge equal to -1/3. And it would give me a baryon number of equal to -2/3. And that's not a thing. Okay, you don't get baryon numbers of -2/3. You've got 3 options for baryon numbers. You've got 1, -1, and 0. You either are a baryon, you're an antibaryon, or you're not a baryon. That's it. Okay, so this structure here with 2 antiquarks cannot be allowed to exist. Now, I'm about 8 seconds ahead of you, so there's going to be a little bit of an awkward pause here. But I want you to take a look at that table, because is there any other combinations that we could play with here that we could actually get interesting stuff out of this? Because some of them are theoretical, and some of them are actually highly, highly possible. So I'm going to stick my little anti-up quark back up here. And what else could we do? What else could we do that we could get 1s and -1s out of here? We picked 3 as a random. Any takers in the chat? We've all gone very, very quiet. That's all right. Let's try this. Let's try this. What about I take this out, I take out my anti-down entirely, and I have, oh no, I don't want to do that, that would be very bad. What if I did this? What if I did an up or an anti-up and a down? So up, anti-down, very good. Up, up, anti-up, like that. Those were 3 up quarks, up, up, anti-down. Very good, very good. Okay, we've got some things going on here. We've got some things going on. Okay, so up, up, up would give me a charge of what? 2? Yeah, 2 plus charge and a baryon number of 1. We've got a nice exotic baryon there, and that is possible. That is possible. We're not going up with that. Up, up, anti-down would give me an up, which would give me 2/3, and then an anti-down would give me -1/3. So I couldn't actually have that. I couldn't have up, up, anti-down, because up, up, anti-down would leave me with a baryon number of 1/3, which I'm not allowed. I have to have a baryon number either 1, -1, or 0. So have a look at this. What about down and anti-up? So a down would give me 1/3, and then up would give me, anti-up would give me -1/3. That would give me a baryon number of 0, which just tells me I'm not a baryon. It would also give me a charge down -1/3, up plus 2/3, or anti-up -2/3. That would give me a charge Q equal to -1. So Q would be -1 and B would be 0 here. And that's allowed. That's allowed within our system. But whatever we've created here now is no longer called a baryon. So we can't put it in this little bracket. So we get rid of that. And once we do this, we've created something different. We have created something called a meson. Okay, and a meson is created when you have a quark and it's an anti-quark pair that creates a particle. Now, remember I said matter and antimatter, when they meet each other, will annihilate. When I say that, I mean when a piece of matter meets its antimatter equivalent. Okay, so a down and an anti-up are not matter-antimatter equivalents of each other. Okay, so an anti-up can't meet an up. They will annihilate. But a down and an anti-up can quite happily coexist together. And these will form mesons. Okay, now mesons are not baryons because they don't have a baryon number, but they do have a quark structure. Right? So we're going to have to put them in a group together. So these mesons, these are not things that we're familiar with. We call the other ones protons, we call them neutrons. These are things like pions and kaons and weird stuff. And what they do is they are involved in the strong interaction, okay, inside the nucleus. So that's probably one of the reasons if you haven't heard of them, you haven't heard of them because of that you're into some serious nuclear physics there. Wait a minute, I hear you cry. Didn't we just say that the gauge boson, the gluon, was responsible for this? Where's this meson coming out of? And it's also involved here in some way. One theory says that the gluon keeps the quarks together inside the proton, keeping everything nicely together, whereas the meson mediates between nucleons and neutrons and so forth. There's a bit going around here on it, but mesons are involved in the strong interaction, and they are formed with a quark and an anti-quark pair. And that's the only way you can get this. It has to be a quark and an anti-quark. You can't have two regular quarks because you get B as 2/3. You can't get two anti-quarks because you get B as negative 2/3. It would have to be a quark-anti-quark pair. For those of you who are particularly keen, there are theoretical pentaquarks where you would have 5 quarks involved, that you could have like an up, down, anti-down, which would give you 4/3 minus 1/3, which would give you 5. They're a little bit off. Okay. As far as string theory goes, we're not going as far as string theory here. String theory sort of goes, well, it's the what if you cut a quark type thing, and everything's made from via vibrating energy. Okay, so here's where we're at. So we're going to call these things, anything that we've got that has a quark structure at all, we're going to call a hadron. Now, those of you who are physics nerds will certainly have heard that word before. Okay. Because there's a very large hadron collider at CERN. And that's what they do. They fire stuff into stuff that has quarks to see what comes out. And your hadrons fall into 2 categories. They fall into the baryon category, where B equals 1 or minus 1, or they fall into the meson category, where B equals 0. Okay, but most importantly, to be a hadron, you have to have quarks inside you. Now, since I've gone on and on and on and on about having quarks inside you, the logical situation is then that there are things that don't have quarks inside them. All right? There are things like, for example, the electron. And it's not very interesting because you've been chatting about the electron since you were probably in first year at school. But the electron is fundamental, the best we can tell. The electron has no underlying function. You'll probably remember this from lower 6th, because once you go into electron diffraction and so forth, the electron starts behaving as a wave, and it's very difficult for that type of thing to have an underlying structure, something that ends up spending most of its time pretending to be a standing wave around the nucleus. So the electron is fundamental. It has no underlying structure, which means it has no baryons in it, or it has no quarks in it, which means it, by definition, has a baryon number of 0, if we were to assign it that. It has a charge, obviously, of -1, as we had before. Okay? But we've got to then identify this, because otherwise we might end up in a situation where we have B equals 0 and Q equals -1. There are mesons that we can build that have B equals 0 and Q equals -1. So we're going to have to give our electron some form of identifier that tells us that it's not a meson, it doesn't have a quark structure. And the identifier we give it is called L. Okay, and we give it the number L equals 1. L for not for electron. What the heck's going on here? Well, the electron happens to belong to a group of particles called leptons. All right, and leptons are fundamental particles that obey something called Fermi-Dirac statistics. We are not doing Fermi-Dirac statistics tonight, okay? But they obey the same laws as the baryons do in terms of their statistical distribution, but they don't have a quark structure, and therefore they're called leptons. Okay, leptons include the electron but are not limited to the electron. There are other leptons, and we need to talk a little bit about them. Okay, so there's the electron, which we'll call E minus, and its alpha particle, or its antiparticle, sorry, I should say, E plus. If I can get the right font. E plus. Okay, so if E minus is the electron, we would have loved to have called E plus the anti-electron, which would have made life really easy, but it's not. It's called the positron. Because, positiveness. Right, associated with that electron, there is something called a neutrino, an electron neutrino, in fact. Okay, now an electron neutrino is essentially it's a particle that is almost massless. I don't want to say massless because it does have mass. It's not a photon. Okay, so an electron neutrino has mass, travels very, very fast, can have charge, but generally doesn't, as far as I'm aware. No, doesn't. Can do. Interacts unbelievably weakly with matter, like ridiculously weakly with matter. It's one of the hardest things to actually discover. It's the hardest thing to detect. You have to put it through vats of heavy water to make it interact with anything. But it is there, and it's the result of, if you do certain experiments with electrons, mass goes missing, or some of the energy goes missing. That energy was then shown to be taken away by this little particle here called the electron neutrino. It gets given the symbol nu, okay, which is like a V but slightly on its side. Okay, and because this is the electron neutrino, because there are neutrinos for different particles, it gets a little subscript E. All right. Now, since each of these particles that we're about to discuss has their own little neutrino associated, we'd like to think that this would be called the positron neutrino that would be associated with the positron, but it's not. It's the anti-electron neutrino, because it's not the neutrino associated with the positron, it is the antiparticle of the electron neutrino. I hope that makes sense. And it is also given the symbol nu, and also given the subscript E. Okay, but like all antiparticles, we'll have to change the font size here because this is getting a little bit out of hand. Let's get that down a bit so we can fit it into the board. Oh dear, that's not so good. We have a catastrophic failure. Give me 1 second, folks. Let's get that going. There we go, we got a full-size one. I've just had a random crash there, and yeah, okay. So we'll come back, we'll get back to where we were. So we have my electron. Thanks, Ashley. Nice to see you again. So what we're looking for here is our electron neutrino. So we have our electron. Bear with me whilst I put back together my board, which is E minus, and my positron. Really didn't like resizing that, which was E plus. My electron neutrino. We will not be resizing this. Electron neutrino. We'll give that its little nu, and then its subscript E. Subscript E. And then our anti-electron neutrino. Anti-electron neutrino. Sorry about the delay there. That's live for you. Okay, and it gets a little nu, and it gets a subscript E, but as with all antiparticles, it then gets the little bar over the top of it, okay, to make it an antiparticle. Okay, hey, we're currently having a Lever Zoom chat. Hope you don't mind if some people can't watch this at the minute. That's absolutely fine, Ashley. Don't worry about it. Don't worry about it. Okay. I don't remember being invited to the Levers chat, but you know, whatever. Anyway, moving on. So we've got electron, positron, electron neutrino, anti-electron neutrino in their situation. And they're the first generation ones, and they're the ones that we're going to end up talking about. Later on, we will discover that there are other ones. There are things called the tau and the anti-tau. And they have a tau neutrino and an anti-tau neutrino. Tau gets the symbol tau, which is nice. Okay, and anti-tau will get tau with a little bar over the top. Okay, and there is the muon as well. Okay, which gets the symbol mu. And then the anti-muon with the symbol anti-mu, and so forth. Okay, so the basic concept there, though, is that these all fall into the categories of being fundamental particles that don't have an underlying quark structure, but do follow Fermi-Dirac statistics. And that makes these leptons. Okay? Right. Now, let's put that together. Because we have, oh, we don't anymore. We have leptons, we have our baryons, or our hadrons, and we have our bosons. Okay, and these are our critical concepts here. What we want to do now is we want to put that into an idea. By the way, our leptons all have lepton number either 1 for the particle or lepton number equal to -1 for the antiparticle, and L equals 0 if you're not a lepton. Okay, so all the baryons have lepton number equal to 0, which makes sense. Now, the reason these numbers are important is because when these things react together, these numbers are conserved. So if I have a lepton that interacts with a baryon, okay, well, the lepton number before is 1. There was 1 lepton. The baryon number before was 1. There was 1 baryon. So at the end of the game, whatever happens in that interaction, whatever comes out of it, must have a lepton number of 1 and a baryon number of 1. Okay, join our Zoom quiz. If it's going on in about 15 minutes time, I absolutely will. I absolutely will join the Zoom quiz. Okay, now let's put this all together. Let's put this all together. We've got a beauty of a diagram to go with this. All right, and here it is. Here it is. If you are a hadron, you have a quark structure. Remember that? There are 2 types of system that have a quark structure. A meson, which is a quark and antiquark pair. It has a baryon number of 0 if you're a meson, and a lepton number of 0, and is involved in a strong interaction. You can generate the various pions from this. Not so important. Pi plus, pi minus, pi naught, and anti-pi naught. Read about that one yourself. You can also be a hadron and be a baryon. A baryon has 3 quarks. So it has a quark structure, making it a hadron. Baryon, 3 quarks. Each quark has B equal to 1/3 and L equal to 0. And we have up, down, charm, strange, top, bottom, and their antiparticles. Anti-up, anti-down, anti-charm, anti-strange, anti-top, anti-bottom. Okay. Up charge has a charge of 2/3, and a down has a charge of -1/3. And we can use that to make protons and neutrons. Okay. Baryons are fermions because they obey Fermi-Dirac statistics. Mesons are not. Mesons are involved in the strong interaction. They are force carriers, and therefore they fall into the boson category. They carry bosons. They're actually called a composite boson as opposed to a fundamental boson up here. They're not fundamental because they have a structure. All right, so let's get this finished off. Our other fermion is the lepton. It is fundamental. It has no underlying structure. The electron and the electron neutrino, the muon, tau, and their neutrinos, and their antiparticles. So the positron, the anti-electron neutrino, the anti-muon, the anti-tau, the anti-tau neutrino, the anti-muon neutrino. They all have B equal to 0, or L equal to 1 or -1, because they're leptons, their lepton number. Up at the top, we have our bosons. These are force carriers. They are things that actually make things interact. The gauge bosons, or vector bosons, as you might sometimes see them written as, are fundamental force carriers. And we have the photon, the W boson, the Z boson for the weak interaction, the gluon, and the graviton in theory. These are our fundamental force carriers. There is, of course, it would be unfair to leave it out, considering the furore that's caused in the recent years. There is a scalar boson that is not a vector boson, and it is called the Higgs boson. We'll leave that where it is because the Higgs is a discussion for another time entirely. And then we have our composite bosons, and there are lots of these. We just happen to be talking about mesons tonight. And a meson is a composite boson because it's involved in transferring force from one place to another, but it's not fundamental. Therefore, it has an underlying structure. Okay, so you are a hadron if you have a quark structure. You are a boson if you transfer force. You are a fermion if you obey Fermi-Dirac statistics. Now, notice that our fermions are basically all of matter that we observe. Protons, neutrons, and electrons all count as fermions, and that's why they deserve to be mentioned here. All right, ladies and gents, on our next one, we'll actually talk about how we use these B's, L's, Q's, and so forth to work out what happens in certain interactions. We're going to look a lot at things like beta decay and beta positive decay and what happens with all of that. All right, but this has been a really rapid run through fundamental particle physics. I hope it's been in some way useful to you. Thank you so much for joining me, especially for those of you who stepped out of a Zoom leavers chat. And all that remains for me to say, of course, is, as always, physics rocks. It's true.